find the equation of the tangent plane to this surface at the following point. Here's how we should proceed. I'd like to start by writing down this function of x, y, and z to be x squared minus 2y squared plus z squared plus yz minus 2. If you're wondering, I'm just copying here. But the difference is that I sent this to the other side. So it's just like saying that, forget about this. If this is true, then that is true. You should agree with me on this. Now I call this f of x, y, z. This is really what I'm aiming for. And this describes some surface. Some weird surface. We'd like to find the equation of the tangent plane at some point. Let's take a look at this point. Maybe the point A is here. And we're looking at the tangent plane, which looks maybe something like this. So it's a tangent plane, and A lies on that plane. If we would like to describe the equation of this tangent plane, then here's what we should do. What we need to do is we need a normal vector. That pops out of this plane. It's normal to it. Normal in the sense that it makes a 90-degree angle with this nice plane that we have here. So this is a normal vector. And I want any I don't want to say point, but let me say any point x on this plane to satisfy n dot product with x minus a to be equal to 0. Why do I want this? Well, let's see. First off, we know that the dot product can be written as the magnitude of n and the magnitude of the other term, which is in this case x minus a, the other vector. By the way, x minus a is a vector. If this is not clear, let me use blue to emphasize that. This is a vector. Good. Then I go on with this construction, and I recall that this is the magnitude of the two vectors times cosine of the angle between the two vectors. Now, if I want this to be equal to 0, and I choose the normal vector to be non-zero, and I choose a point which is not a, if I choose another point that's not a, then this will also not be 0. Then this would imply that my cosine of theta is equal to 0, which would imply that theta is equal to pi over 2, or you could say 90 degrees. And if theta is equal to 90 degrees, then this point is on the plane because it is adjacent to A, meaning that the angle between this blue line, this blue line here, and this n is also 90 degrees. So that is basically a recipe. This precise statement is a recipe for us to find a tangent plane. I mean, well, any tangent plane in principle. So that is very good. This is what we will be using to agree on this. Now, this is not necessary for the solution in any sense or in any way possible. All you need to do is to know this. And the goal from the last 5 minutes and 51 seconds was to show you how you can make sense out of that. So this is the formula. If you know the formula, you can move on. If you don't know the formula, now you know it. We have our vector A, and our vector x is the parameter for which our candidates must satisfy. So if I choose a random x, it needs to satisfy this equation. So this is not something I should play with. But what's clearly missing here is the normal vector. So how do I find the normal vector to this plane? And the answer is take the gradient. And not just the gradient, you take the gradient at the point A. So in other words, we want to take n to be the gradient of f at the vector A. The vector A, this means at 2, 1, minus 1. That's really what we're looking at. For that, we need to compute partial f, partial x, partial f, partial y, partial f, partial z. That is going to be, if we take a look here, it's going to be two x, because it's the only term that changes with respect to x. The second partial is going to be minus 4y plus z, since these two terms are the only two terms that change with z, with y. And for z, we'll get 2z plus y, since these are the only two terms that change with z. All the other terms are constants and are treated as such. Now notice that we're looking at the value of this vector at 2, 1, and minus 1. And so this is something we can evaluate. I think now it's a good time to minimize this part. Not everything got captured. I don't like this tool. I like the other one, the one with the rectangle. But the problem is that I cannot use it now because it's too wavy. I don't know what the word should be. Anyway, so when I plug in 2, 1, minus 1 for x, y, and z, I get 4x. Well, I mean, just 4. There's no x there. And then I get minus 5. And then, minus 4 times 1, minus 1. And then finally, I get minus 2. Because this is minus 1, and then I'm adding 1. So minus 2 plus 1 is... see? I already made a mistake to So z is minus 1, y is 1. That's minus 1. 2 minus 1 plus 1 is 1. Minus 1. Anyway, so regardless of my basic arithmetic incompetency, let us proceed. Now we have our vector n. We have our vector, well, our point A. It's a vector, but in a sense it is a point. And then we write down the equation more precisely. We get 4 minus 5 minus 1. Take the dot product of this with the following vector. So I'll take the vector x to be constituent of x, y, and z. I hope that's fine. So I get x minus the first coordinate of A, which is 2, then y minus the second coordinate, which is 1, then z minus negative 1, which is positive. And now this should be equal to 0. I expand this to get 4x minus 8 plus minus 5y plus 5 minus z minus 1. In the end, this is going to be equal to 4x minus 5y minus z plus or minus 4, if I'm not mistaken. Exactly. So this in the end will be equal to 0. If you want to maybe write the constant on the other side, then you can simply write 4x minus 5y minus z is equal to 4. Now this 0 didn't appear out of nowhere. It's literally from here. So I was expanding. So I was expanding the left-hand side, but let's not forget about the right-hand side. So these all these terms are equal. And if that is true, then this should be the answer for our problem. I hope this was clear. And from my side, I don't really have anything else to say.